Welcome everybody, thanks to be here. So the speaker of today is Gaspar Galaz, who is now professor in La Católica, Santiago, Chile, and is an expert in low surface brightness galaxies. PhD and into La Serena talk.
Yes, talking and currently. Yeah. Thank you for this opportunity and for being late. And also probably. Okay, there, it's okay. Yeah. So some models, early models. And then I will rapidly to go to the iconic case of Malin 1, which is in fact is the biggest galaxy, the biggest spiral galaxy detected so far as a single entity. Okay. And then I will talk about some other projects and collaboration and conclude. Okay, so let's talk about the rise of this subject. So early discoveries, perhaps some of you know this, was the starting point was a little bit in 1970 when Ken Freeman discovered that the spiral galaxies, these galaxies in plates, photographic plates, appear to have some sort of threshold in the surface brightness. Okay, that was about 21.65 in B. So that, of course, attracted attention because could be a physical effect, an actually physical effect of having this threshold. And of course, well, afterwards, Disney in '76 proved that this was just a bias produced by the photographic plates. The photographic plates, most of us have never use these photographic plates for doing astronomy, but of course, then you cannot track the sky. You are summing up everything, the sky, the object, everything. So you are adding to the signal of the sky to the signal you want from the objects. So in principle, if you reach an object that is below the sky, you are losing it and it will appear that at the end you will have the same sort of brightness of the sky. Okay, so Disney proved this bias, and then in addition predict the existence of a lot of low surface brightness galaxies of this kind in large numbers. Okay, and then perhaps this is more familiar for all of you. This is the famous paper of Ken Freeman on the disk of spirals and S0 galaxies. Also S0s. We always forget about this important type of galaxy. And then it concludes this threshold that paid attention to many people. Okay, and then this is the construct of the paper of Disney in Nature in 1976. This is the threshold, and of course, it started in a very strange way. Imagine that we are living in the center of an elliptical galaxy, and in that extreme way to show that the sky will be completely full of stars and the surface brightness of the sky will be very, very high, and then we are going to live in a very different observable universe compared to what we see today in our place. Okay, so that motivated a search a little bit for more astronomers for more galaxies, this kind of LSB galaxies, and that started around 1985 with photography plates. Okay, and then Botun and some collaborators discovered an enormous disk galaxy that was that Malin 1. This is a story behind that. Perhaps I will have time to tell you. Okay, and then this is the paper where they discovered, they informed the discovery of this big galaxy. And this is very interesting because when they discovered this galaxy, okay, it appears like this. Okay, that one you see there is probably the point, not a stellar point, but with something that when you use very deep images like the one at the right, you start to see, thank you, you start to see where's the thing? Where's the laser key? There. Yeah. There. Thank you. So you see a very diffuse disk. Of course, here you see nothing, and then you see this. This is a MGC 4571, which was some sort of nightmare for some observational astronomers. But many people at that time go to this galaxy, for example, in radio, and you know that sometimes in radio it's difficult to point the things. And of course, they finished to start observing this one. We're very happy with the signal. Okay, so everything changed when they proved with H1, 21 centimeters, that the galaxy was very far away, much farther than this one, about 20 times farther than this galaxy. And so when you see at that time this size, you conclude that the galaxy is really large. Okay, it's at least 110 kiloparsecs diameter, which immediately places this galaxy as the biggest galaxy at that time. Okay, that then was the important thing. Okay, so after this paper, many researchers turned to their attention to the systematic search of these galaxies, in particular giant ones of the kind of Malin 1. And then after, I would say, almost 20 years, 15 years, they compile a set of properties that were pretty much common to many of these kind of galaxies, and in particular to the giant ones. Giant means typically this is something that is not written into stars, right? But with diameters larger than the Milky Way, more than 50 kiloparsec diameter is considered a giant LSB. The extreme ones, like Malin 1, are very few. The next one is about perhaps 120 kiloparsecs instead of 200 kiloparsecs. So immediately you descend to the list, and so I will talk about the efforts to discover more of these galaxies. And so just to go fast, the most important features of these galaxies is that they have typical enormous amount of H1. So the reservoirs of H1 here is huge. Okay, much typically more mass in H1 than in stars. Okay, they have a very flat rotation curves. Okay, they lack usually of molecular gas or very difficult to detect. Okay, they have redder colors than this population of normal smaller LSBs. Okay, they have also a very extended rotation curves. I already mentioned this. Okay, large mass luminosity ratios, and they usually, this is something that the last I would say 20 years, 15 years, that was more solidly established, that most of them are located in low density environments. Okay, this is important. Here you can see a set of rotation curves or different. Sorry, this is the H1 surface density as a function of the radius. Okay, this is just to show that the surface density of H1 in these galaxies is just at the critical value, okay, given by Tumblr, or at or below. Okay, that this is very important because it's the key to understand why these galaxies in general, first of all, are not forming stars. And of course, there are many theories in which the molecular gas is even lower density. It's at the even lower density than you can see here. Okay. Okay. This is also an important that appears not. Regular ones this way to okay okay
Sorry for everybody online, we're having technical difficulties.
See that Ben?
Yes,
Switch off the camera. So that might help.
want me online?
Might.
there. Okay. Apparently, yeah, that was the next one. So it's a miracle we finish on time. So properties of these galaxies, this is just a display of the properties I mentioned before. Okay, here you can see NGC 289 with an amount of gas which is largely superior to the emission you see in optical. Okay, this is a plot by O'Neill and Botton in 2000. There, just to show that the volume density of the universe, if you take any volume density in the universe, an average, you will see that most of the galaxies in the volume are low-source brightness galaxies. Okay, so that's why it's important to study these galaxies in the first place. Okay, so then I will talk about models in the outline. Okay, so one of the first efforts to model the formation of these galaxies was made by Hoffman in '92. Okay, and the interesting paper, the thing of this paper, I invite you to see this in more in detail, is that they tried to understand the formation of a very low solar brightness disk from first principle. No simulations, PNG, whatever, nothing, just first principles, and they arrived to form a very low solar brightness disk for galaxy. Okay, I can't tell you more details, but I don't invest more time. So then Noguchi, okay, also predict the formation of a very low solar brightness disk using disk instabilities. Okay, and that using, by the way, using the formation of a bar. So you form a bar, and then the bar establishes some instability in the disk, and then the disk spread out outside the main part of the galaxy. Okay, that was perhaps some of you remember, this was the time between 2000 and 2008, perhaps, that many people try to understand many features you see in galaxies using bars, okay, and modeling the bars. Gia Tanasula was one of the most enthusiastic persons on this. Then Mapelli, in 2008, proposed that LSBs could be formed by ring galaxies. Another thing that appeared in the history of this subject. Okay, but the problem that was not an indication of fat rings in observations are observed. Okay, so that was a very beautiful way to understand the formation of these galaxies. Okay. Okay, so then in more modern times, okay, Su and 2018 use Illustris PNG to find a unique disk galaxy like Malin 1. So what they do is they go to TNG, I think was TNG 100, and they see the galaxies that are there, and they found this. They follow the tree in the history, and they found that was produced by the collision of two galaxies that they call intruders to a one central elliptical galaxy, and then the result of all of this interaction is to form a very big disk like the one you see here. Okay, that's very interesting because you can trace the evolution of the molecular gas, the atomic gas, and other things. Okay, the rotation curve, etc. Okay, and it's very similar to Malin 1. Then in 2020, with a postdoc, we try to make something similar, but with Eagle, which is a similar model but different technicalities in technical things different from Illustris. And so there we show that there is a significant fraction of LSBs that are formed, giant LSBs that are formed, but are easily destroyed if they form in medium-rich environments. You don't reach really a really rich environment, but even really medium environments in richness, you easily destroy these galaxies. So if you can say prediction of this, is that there were many of these galaxies in the past, but in the last 1,000 billion, 1 billion years ago, they were destroying this in these environments. Okay, some galaxies were very similar to Malin 1, a little bit smaller, I would say. Then Su, again, in 2023, this is more recent, it tried to reproduce many observables you see not only in these galaxies, but also in other these galaxies, in particular to reproduce or recover the 2013 result about the scaling relation of the size of the H1 disk and the mass. Okay, that's very interesting work. Also, he reproduced this placing Malin 1. Well, Malin 1 is there. Other very famous giant LSBs like UGC 6614, Malin 2, and 1382 are there. Okay, so you can see there in red the simulated galaxies by Illustris. Okay, and the observed ones. Okay, these are early observations of LSBs. Okay, so let's go rapidly into the case of Malin 1. So I will not repeat this. Okay, it was discovered in 87. Okay, so one interesting thing of this galaxy that has been studied reasonably recently is that this galaxy is not alone. There is is interacting with galaxies. There are two small galaxies interacting in the center of Malin 1, and another one which is a little bit farther away. I will mention. Okay, sorry, this is I get confused myself. This is because I'm trying to go fast. This is Malin 1. Okay, here you see the disk, and if you go to deep images, you see this one. Okay, so the difference is really notorious when you see deep images like the one we observed in 2015. We published this. Was the first time, I guess, that was the reference says. I wasn't even not realized that, but was the first time that we see the spiral arms with so clarity. Okay. Okay. So yeah, and the other interesting thing is, I was saying that there are three galaxies. Two of them sure, another one which is not clear, but everything seems to indicate that. This galaxy here and this one, these two dots, okay, are compact galaxies in the disk of Malin 1, and a third one, which is this one, with exactly the same redshift of Malin 1, okay, and you see a stream. The thing is connecting the Malin 1 with that, okay, at least visually. So I have just, I think it was before yesterday, a student of mine, a PhD student, sent a paper to AstroPH, you can see it, about the dynamic past of this system, okay, using n-body simulation. Okay, but this is some publicity that is not to. Then, okay, so just to compare, okay, just some few after we published that paper on 2015, Samuel Boissier published a paper on Malin 1, but more focused on the stellar formation history of this galaxy. Okay, and here you can see what the models use UV bands and infrared, but most of it was optical and UV image from galaxies. So they show that you just have a formation of stars at the beginning very rapidly, and then the formation is stopped. Seems to be very basic, huh? But when you see the process is not so very. This is the star formation rate, surface density, the surface density of the gas. This is the surface density of the stars, okay, etc. And this is the metallicity. So the metallicity evolves up to the metallicity of about a little bit less than solar. Okay, I will show you more results. This is another thing to keep in mind. This is the gas, which is near 5 solar masses per square parsec. That I will show that it's pretty much what we see with ALMA, okay, in the center of Malin 1. Anyway, so then we start to make a campaign. We joined forces with Samuel Boissier, instead everyone at his side. We tried to go things together. It's a small group anyway. So we have observation from MUSE with the VLT, and we could observe. In fact, the plan was to observe the whole galaxy, but for some reason they just observed this. There were problems with the instrument at that time, and it was in the middle of the pandemic. So, but in March, so in some few weeks, they are going to observe the rest. We got more time applying again. You know, the process is terrible sometimes. So these are from Junais, who is the first author. This was a student of Junais. And when he published this was postdoc in Poland, in Warsaw. And these are the results from MUSE. So here you can see the emission lines, H-alpha, H-beta, O3, and N2. So the first thing, of course, you see is this is not a boring dying or something like that galaxy. You have, for example, H-alpha. This is the central part. For those who have a better eyes than me, perhaps you can see a double nucleus, which was studied by another collaborator in the group, Evelyn Johnston. Okay, it's very interesting. Yeah, this is the H-alpha spots. So the first interesting thing is that there is a lot of H-alpha spots in the disk of just 1/4 of the galaxy. Okay, so we are really excited to see the rest of the galaxy, what it will bring this observation. There is a large clump of H-alpha here that even you can see something in the optical images, etc. Okay, and all the lines true. There is a paper that should appear in the next month by the first author should be Benoit Binat from LAM in France about the kinematics of all the disks in Malin 1. He's really expert on that. So we're trying to focus on different things and different researchers where the expertises are higher. This is very interesting. This is the cell formation rate in the different spots, average as a function of radius. So you can see that the stellar formation rate of Malin 1 is small. It's not, of course, large when you compare to other galaxies, but still there, okay? Except in the center. So this pretty much show what Aaron Barth, another researcher in 2007, show, as you can see, many of these very giant galaxies, that the center of these galaxies seems to be a really independent entity, okay? It's like, well, the center of Malin 1 is like our galaxies. So it's a little independent spiral galaxy rotating, and the rest is pretty much unaware of what is happening there, okay? And this is shown here pretty much some way. The differences are enormous, okay? When you see the difference in stellar formation rate in the center and in the periphery is another story, okay? Okay, so this is to the metallicity. We're right to compare the metallicity at some point, okay? And this is the surface brightness. Okay, so we are really reaching very fine surface brightnesses in the whole galaxy, okay? It's not so metal poor as some people sometimes believe, okay? And then, Evelyn Johnston showed this discussed this double emission source we have here in the center. This galaxy is also linear, okay? So there is an IGN inside here. So there is a lot of discussion about the nature of this source. We have the hypothesis, which is a nuclear stellar cluster, but of course it's not really easy to understand this when you have a linear in the center. Okay, we are asking for more more ALMA images. I didn't reach this part, but more ALMA images and also MUSE with the adaptive optics to see the center part in particular. So this is other things we are exploring with the student. This is the thing which appeared in AstroPH 2 days ago. The paper is not accepted, but the student commit a little error and sent to AstroPH. So anyway, things happen. But if it's okay and things are happening as we expect, should not suffer too many modifications to the acceptance. So this is what we are studying. The idea is to use n-body simulations to see the possible orbits that fit with what we have in spectroscopy, okay? And basically spectroscopy where we have the radial velocities of the components, and try to see what are the most probably path you can see in the movements of these 3 galaxies. This one, which he called exomalin 1, and the 2 galaxies embedded near the center. Okay, so you can see that in AstroPH. Okay, then I was mostly in charge of this part in the collaboration, was to search molecular gas in this galaxy. Okay, this was a campaign that in fact started many years ago, when the galaxy, the astronomers realized that was the biggest galaxy in the universe, Spiral 1. Of course, they want to have a lot of information, and one of them, very critical to understand, is the stellar formation. And for that, you need CO, you need molecular gas. And then they start to see that in 1989. Bottom again, okay. This was the champion of LSBs at that time. I think that he left the field, but you never know. And then Radford also tried to understand, I mean, to detect the CO. Most of this was done by Iran, okay, some of this, and also with the radio telescope at West Virginia. You know that West Virginia, if you have been there, the only way to have really dry air is to observe in winter, okay, and it's not easy at all. So the emission, the water vapor is very high, so it's the submillimeter observations are very difficult. And then Brain using Iran, O'Neill again, Musumi Das, and myself using the GBT. That didn't take anything. So there were other searches not published, Patricia Nesek in 93 and Leslie Sage in 95, etc. So what you see in all these papers is this, nothing. Yes, no. Okay. That tends to be a little bit of obsession of many astronomers to search and discover molecular gas in this galaxy. So finally, this is GVT for those who are not. Okay. So finally, we use MALMA in March of 2024. I have to confess that this was the proposal number 3. Present proposals were rejected. Okay, so at some point, and anyway, so finally at the third effort that was possible to have time, and then they detect the CO 1210. Okay, and the center of the galaxy, as was predicted, because there is more probability to find CO, but also we observe in many other places. In fact, we use the interferometer to detect CO in all this area, okay? And we detect with a very high signal. That is very interesting because it was not a small signal. And we detect the line there, and the continuum. Both, and the continuum was very high. We published this in November last year, and there is a small discussion about the nature of this continuum emission because it's very high. It's very high. So. Okay, this is the line. As you see, it's not a very small line. But of course, when you see this and you compare to other lines, you observe it typically in the galaxy and in other star-forming galaxies, this is smaller. Okay, it's similar to noise. We detect also other emission. Okay, and when you see these other spots here, and there in the disk. When you see this, it's not associated to any H-alpha emission or optical emission, okay, or optical emission. And the other thing, but this is the worst, is when you see the lines are not really weak, okay, but the problem is the velocity when you detect this. All of them are shifted about, the best one is 99, sorry. That in the publication, we named these galaxies tentative emission because we are not really sure where this emission comes from. We suspect that it is from the disk. Yeah, in a galaxy of 200 kiloparsecs with a rotation curve that reaches very high velocity at the end, perhaps you can expect that the velocity dispersion is very high for the components in the disk. Okay, so this is another thing we want to prove with new observations.
Sorry, but you're looking at this galaxy virtually face on.
Yeah.
How can you detect the rotation of 1,000 kilometers per second? I'm
Yeah.
missing something? Wow.
No, it's very strange. That's why, okay. So here we just inform about this.
Okay.
Okay, but we believe there is a if you see the rotation curve in rotation curve, it's not completely phase on. It's like this. It's perhaps 30 degrees. If you see the H1 emission, you will see that it's a warp, very strong warp. Okay, so and the warp is about 200 kilometers per second difference in difference. Okay, so this is more. This is the problem. Okay, but this galaxy has so many weird things that anyway, but I agree. So this is we build a chemical Schmidt diagram for the molecular gas. So this is the surface density, mass surface density of the molecular gas, not the total gas. And when we trace with ALMA the surface density from the center in different annuli, okay, we start to see how this stellar formation rate changes from the center there up to the most distant isophone annuli from the center of Malin 1. So the stellar formation rate decreases from this value, which is quite high, compared, for example, from the fast galaxies that are normal spiral galaxies. Okay, it's very similar in the center, up to the end. Okay, where you see really small values for the stellar formation rate, surface density stellar formation rate. Okay, this is not the periphery. This is the center. The end of the center. I should be more precise, perhaps, to see. Yeah, this is the thing. So this is the center of the galaxy. Okay, so the last values, the slowest values are there. Okay, things that are near the end of the center. Okay, but anyway, in the center part. Yeah. Okay. You can see other galaxies. This is Malin 2, for example, and this is UGC 6614. Okay, which in fact is one of the few giant LSBs with detected molecular hydrogen. Okay, well, molecular gas. So, okay, this galaxy, for example, is not really has not a very low stellar formation rate. Okay. Oh, this is so a little bit old. This is the paper we published, and there are more things. So another thing, we have other projects and collaborations. Here we are finishing. This is another one led by Michel Berg at the Texas Christian University in Fort Worth in the United States. He got time with James Webb to observe 7 hours using MIRI. Okay, and the idea is to use the polyaromatic hydrocarbons, okay, bands. This is mid-infrared, okay. And why? Because many of these galaxies show seems to be polyaromatic hydrocarbons dominated. Okay, this is a work, even Malin 1, 2. This is a work made by Nurur Rahman in 2007 when he showed that using Spitzer. Okay, so inspired on that thing, we try to we are trying to do this. These are observations that, of course, are coming in a few months. Okay. And the idea is to characterize the lower end of the Koenig-Schmidt diagram. Okay, and the knee you see in the typical relation for spirals, what you see here for very low surface dryness when the density of the gas is very low. Okay. There are many things that I could discuss, but I don't have time. So another thing that was already published almost 2 years ago is a comparison between the giants that are discovered using the Subaru pressuring. Okay, it is in collaboration with Anna Saburova and Igor Chilingarian, former postdoc I have. And the idea is to compare what the models gives and what the observations give in this area of the hypersupreme camera survey. Okay, and it's interesting because pretty much we are discovering not this amount of galaxies, but we predict in the whole sky up to C.1 about 12,000 galaxies. Okay, that should be discovered if this is true. Okay, of course, with the LSST, we are expecting to have these galaxies inside. Okay, but it's the other one. Okay, another thing in which I am collaborating is the Condor Array project. The PI is Ken Lanceta from Stony Brook. They have these typical telephotos, inspired, of course, in the project by Dragonfly. Okay, many years ago. Okay, so this telephoto array in the northern hemisphere in New Mexico, and there is another one which is installed in this week. This week is installed in the Parque Astronómico in the northern Chile. With this, we are going to have the whole sky up to very, very low solar brightness limits, 31, 30, something like that. Okay. If they don't put an industry of green hydrogen in front of the coast, like perhaps you are aware of that. Okay, I think this is all. So conclusions. Thank you very much. I'm sorry.
Is there any question for Gaspar? Yeah, okay.
I have a couple. First of all, I would like to come back to the point where you said that those galaxies are fragile, are susceptible to being disrupted by the encounter, so they can't live in even moderately dense environment. And I was wondering, what does it mean they are destroyed? They are disrupted into small chunks. They are transformed into high surface brightness galaxy. What is the process?
Yeah, that's interesting. What we observe with the Eagle model is that they are break up in more smaller galaxies. Okay, and they finally some which are in rich environments, which are clusters, begin to form part of the cluster, and the center of the galaxy keeps like a spiral galaxy, a normal spiral. So it's like the disk is disrupted.
Okay, it goes into intercluster population and nucleus remains as it. And the other question is, in this day on the archive, there was a paper, I think then Van Dokken was one of the authors, about this galaxy, this ring galaxy with 9 rings. I think that there may be some kind of connection here also considering the Mapelli model.
I hope. Because the idea was very beautiful.
Because if you look at the image, it looks like a spiral galaxy to me.
Yeah.
This galaxy with 9 rings.
I have to see that. I was traveling in Florence.
So this was just a comment.
Yeah. Thank you for that appears in the days before.
Yeah, this week I was.
Okay. Yeah. He was the first author.
No, it was the third or something like that. But I cannot swear because
Anyway.
I remember the image but not the names.
I will look. Thank you.
Yes.
Very, very nice talk. I have some questions about the CO observations. Were you expecting, given the H2 clouds that you found, that you could observe the CO counterpart? And so was it surprising not to find CO clouds close to the H alpha emission? And about the very fast, let's say, CO observed clouds that you find, could they be, maybe given the fact that you studied the orbits also of the companions, maybe something dragged out of the disk by the interaction with the other galaxies then pulling back? I don't know.
Yeah. Yes, that could be done perhaps. But for that, the problem of these galaxies is that you really need with ALMA we think is not very difficult compared to other projects that use a lot of time. The problem here is perhaps what I'm going to say is not politically correct, but you have to combine the time allocation committee to would say 20 hours or something, 30 hours for just one galaxy. And that is very difficult. Because now the time allocation committees are working, both in ISO and ALMA, are working with this peer review. So 10 people see your thing and they put scores. It's very difficult. It's really, it's not easy to get time. But yeah, so here one thing that could be done is to observe these spots with perhaps with a single dish telescope with more time and try to see if there is something there. Okay, this is one way. A big one, okay, Iran perhaps, even and also with ALMA, trying to get more information there. But just for one of these clouds, if you need a little bit more resolution, you need a lot of time.
Yeah.
Okay, so that's the, but could be done. Yeah.
Other questions? Yes, please.
Since you mentioned an EGN, I was wondering whether you would try with X-ray observation also.
No, not at this time. But yes, this is another thing that could be done. It's a linear, it's a very low emission region. It's not really. People have, well, there is a spectra from the center, optical one, and you see the line here. You see the typical spectrum of it's almost a textbook linear. Very, very weak one. It's not really, but that can make things. For example, the 3 gigahertz emission is huge in the center. Okay, so yeah, it's not. So yeah, the AGN here should be better investigated. For example,
But are there other low surface
the
brightness
spectral
galaxies?
index is not completely clear here because people have not studied yet. It's not.
Are there strong evidence of AGN in other low surface brightness galaxies? Or not?
Well, that's, yeah, there is a discussion. What you see in the literature is that compared to normal high surface brightness galaxies, AGNs has 10–20% less of AGN compared to in population compared to the high surface brightness galaxies. Okay, but numbers are, I mean, roughly speaking, is very similar. There's no really strong differences. Okay, which is important because one of the phenomena, one of the physical effects that has been proposed to reach a galaxy where the stars, I mean, the gas is not forming stars, is to have a high AGN that truncate the star formation process. Okay, but it's not clear.
There are
If you
people.
switch on the chat, there are a couple
Oh yes, we are in Zoom also.
of questions. Yeah.
Maybe I missed one point. Did giant that
Federico Lely,
let's stop.
wonderful.
Let's see. Down. Yeah.
So,
Federico has another question before, no?
but
No.
the first one is maybe I missed one point. Do you read it?
Yeah, maybe I missed one point. Did giant gLSBGs better fit by
Simple
simple
star
star population models, or you have evidence of different surface star formation episodes?
Long time ago, together.
Yeah. I don't know exactly, but Boissier showed that Samuel showed that this you have an instantaneous burst first, and then something that is not completely cut off, but a smaller stellar formation. Okay, so but he used galaxies. Okay, he used data from galaxies, which I think these people didn't have at that time. So perhaps that changed a little bit the scenario, I guess.
Then Federico Lelli. I have a
About
little.
Mapelli's formation model, the main problem is that creates significant radial motions. but not strong radial motions are seen in the H1 kinematics, which is instead a regularly rotating symmetric disk. Yeah, it's true. Yeah, yeah. Thank you.
I'm curious about the Condor,
The what?
the telescope, was it called Condor? The project, you showed lots of telescopes in a pack.
Ah, Condor,
Telephoto.
Condor, yes, Condor. Yeah.
My accent.
No, no, it's
What's the advantage of having all the telescopes? Like in a array like that?
Yeah, the idea of this array is pretty much the same as Dragonfly. This is not just because it's an array of telephotos, it's that the telephotos has a special coating in which you can have really smooth sky. The flat fielding of this is exquisite. Okay, and you have, of course, big field of views at the same time. So having a very uniform sky and a very big field of view is the difference. Makes all the difference to discover large structures, scale structures in the.
And they are unobstructed. They are not reflector.
Exactly.
You have no
Yeah, you
obstruction.
don't have reflectors.
I see.
Yeah, thank you. Yeah, you have just the light enters and diagonally pass through lens, but diagonally
Goes
to the.
to the detector.
There could be some of one. Okay, there are some people looking. I mean, they're doing a project which is called Castle. Okay, and what was the idea of another project called Messier that was put down by CNES, but that's another sort of story, in which you have mirrors without any lens. Any lens. Have a series of mirrors without any lens, and the mirrors are deformed. And that would be a bomb, but well, that was. But Castle, which is a project led by people at LAM, they are doing that.
Okay, but the mirror must have the focus out of. Okay,
Yeah, exactly. That's right.
to be unobstructed.
So, but the key feature of these telephotos is not the fact that telephotos. A little bit about that, but is that the coating they have put it into the lenses that allows you to have a very uniform. I think it's less than 0.01% variation along the field. So.
Other questions, curiosity? If not, we thank Gaspar again.
Hard for this.
No, don't worry. It's all right. But finally, we succeed.
Yeah, thank you
That's all
for keeping.
Thank you.
In the.
Is this guy here. You see, and
Oh, bye,
there are
everybody. Sorry for the technical.
very low super brightness
Yeah.
part of
Yeah.
those